All right, so this is going to be a lecture on models for ordinal data. All right, so what do we mean by ordinal data? Here's just the quote from Wikipedia. Basically, that's data that's on a numeric scale, but where the scale itself is arbitrary, except that it tells you the ordering of the data points themselves. All right, so here's some examples, some that we've already talked about, right? This product ratings. Certainly, 5 stars is better than 4, is better than 3, is better than 2, is better than 1. But there's not really any meaning for the fact that those stars differ by 1. Right? Similarly, if you ask somebody, this is an often thing if you go to the doctor, they will ask you, what's your pain for this particular thing that you came in for on a scale from 1 to 10. And you're supposed to tell them some number. Right? And it's not clear that 7 is 1 more than 6 is 1 more than 5. It's very arbitrary. This is a common, on surveys, it's common to have things like, how much do you agree with this statement? You either agree, disagree, strongly disagree, these types of things. Right, so these are all examples of ordinal data. So there's an ordering to the data, but the difference between the categories isn't very clear. Right? So essentially, by using the normal distribution we used last time, you do assume that there is some relationship between a 1 and a 2 and a 3 and a 4. Right? That is that they're equally distant from each other. Right? So we're going to relax that assumption today. All right, so feel free if you have questions, let me know. Ordinal data. Hopefully you're familiar with ordinal data. Okay. All right, so now we're going to build a model for this ordinal data. All right, so let's first let yk be the number of observations that you have in category k. So the whole time today I'm going to be really thinking about this example of Amazon product ratings in terms of 1 to 5 stars. Right, so y sub 1 is just the number of 1-star ratings for a particular product. Y sub 5 is the number of 5-star ratings. Right, so we can model this having a multinomial distribution. Right, so y, here's the vector from y1 up to yk, and it has a multinomial distribution where here's the likelihood, at least proportional to the likelihood. Right, so that pk is going to be the probability that somebody chooses the kth star rating. And then the exponent there, yk, is just the number of those ratings that existed. Okay. All right, so the only restriction on this model here is that the sum of these probabilities of which category you pick sum to 1. Right? Every observation we see had to have been in at least one of the it can only be in one of the categories. Right? So this is fine. So far, we haven't really described anything having to do with ordinal data. Right? This multinomial model could have been with unordered data as well. Right? So the next thing is that we're going to build in to the model this ordinal idea. And we're going to do this by setting pk's to some particular value. And it's going to be this value here. All right, so we're going to assume that there's some sort of normal distribution with some mean theta. I guess normally I've been using a pipe here rather than semicolon. I'll fix that. So some mean theta and a variance of 1. And we have these cut points, alpha, in this case, alpha 0 up to alpha k, capital K. In the Amazon product, there'll be alpha 5. So alpha 0 up to alpha 5. And basically, this integral is just the area under the normal curve in that interval from alpha k minus 1 up to alpha k. So we might write this like this, where now this capital phi is just the standard normal cumulative distribution function. Right, and so further we're going to then define alpha 0 as being negative infinity and alpha 5 as being positive infinity. All right, so I'm going to show this in a second in a picture. Is there any questions before I move on to that picture? Why I chose a normal? So I was not planning on talking about why I'm going to choose a normal here. You don't need to have it normal. It could be something else. Later, so the reason I'm bringing this model up now in the semester is that we're going to be coming back to it quite often. And in particular, when we start talking about Gibbs sampling and introducing data augmentation with a latent variable, then this normal is going to be convenient. But there's no reason that it would have to be normal. All right, so let's look at the picture then. All right, so this is, I'm thinking now of the particular example of Amazon ratings where there's 5 different star categories. And here's the picture from this model. All right, so we have alpha 0 is at negative infinity, alpha 5 is positive infinity, and we have some other values, alpha 1, 2, 3, and 4. So far, you're just thinking about these alphas as being known quantities. All right, we're talking a little bit about how you'd go about estimating them. And now we have some normal distribution, and its mean is theta. So it's whatever it is. In this case, I made theta be between alpha 2 and alpha 3, but it could be anywhere. And then what we have is for the product ratings, which are shown in green, right, this is the star ratings, the probability that somebody chooses a star rating of 1 is just the area under this normal curve that's left of alpha 1. The probability that somebody chooses a 2-star rating is the integral under the curve between alpha 1 and alpha 2. Similarly for 3-star, 4-star, and 5-star. All right, does that make sense? So if we have this setup where we know the alphas and we know the theta, then we have fully defined our multinomial likelihood, right? Because we've defined every probability. Right, so yep, just repeating what I said. Okay. All right, go ahead. Right, so yeah, so in this particular example, the rating of 3 looks pretty highly likely. Right, the area under this curve is certainly more than area under 4 and under 2, and it seems like it's going to be more than 5 and 1 as well, yes. So I did, just for the purpose of making the picture, these alphas are equally spaced, but that's certainly not a requirement. Right? So for instance, I think people have remarked in the past that people often in these Amazon ratings, you see the extremes. Right? You see lots of 5-star and lots of 1-star ratings, but not as much in the middle. Right? In particular, not too many 3-star ratings. Okay, whether or not this is true, but you might observe this in certain circumstances. One second. And so what would happen here is that when you estimated these alphas, you would find alpha 2 and alpha 3 be very close to each other if not many people used that 3-star category. Because then the area under this curve is going to be not very big for that 3-star category.
There are a bunch of models of vacuum where the distribution is U-shaped. The counts are U-shaped. There are a lot of 1-stars and a lot of 3-stars. There are quite a few of these. So what if we estimate the variance for this thing as well? If we increase the variance, we'll increase the mass and the tails, and we could probably model that situation better without having to break the normal model and do something more complicated.
So absolutely. Right now I'm only talking about one product. Right? And if we only have one product, then there's an identifiability constraint that I wasn't planning on going into too much today, but I will go into in the future, that you could not just add a variance in here if just one product. All right. With multiple products you can, but yes.
If we're going to estimate our alphas, is there a reason we choose a normal distribution instead of just like a uniform?
Right, so yes, so the question here was about if we're going to estimate the alphas, why bother with the normal, why not have something like a uniform? Yes, I mean, in this example, no. Going forward, this normal distribution is going to be convenient. For example, doing Gibbs sampling with data augmentation. It's going to be convenient if we tried to throw in explanatory variables, covariates, into the model. Right? Then you can move this mean around in a way that you can't adjust that uniform. So for one product, for what we have now, we could certainly use a uniform. Right? But going forward, this normal curve is going to be helpful. Even when we get into multiple products here in a second. Other questions? Okay. So there we go, multiple products. All right, so now we have YKJ, where Y for, let's see, category K and product J. All right, so we're going to have now a multinomial distribution for each product. All right, so each product itself is going to have an independent multinomial distribution. And now there's going to be a different probability for each product and category. So category here being the star rating, for instance. All right? So what we're going to do then is we're going to, again, now we have, okay, good. This, right? We have to have these probabilities summing to 1 over each product, right? So each product, those probabilities are going to sum to 1. And now we're going to define these probabilities for the kth rating for the jth product as being the same normal under the same, let's see, the same cut points, but there's going to be a different normal curve for each product. And that normal curve is going to change by its mean. And now, as was pointed out before, there is a possibility here that we could generalize this more and have some variances be unknown. Right? But we're not going to do that today. We're just going to fix the variance at 1 for simplicity. And think about each product's mean changing. All right? So if we expand this out using the standard normal curve, that's what we have. All right, so the way that we're defining it today, there's the same alpha cut points over all products, but each product has a different mean for their normal curve. All right, so let's look at that as in a picture. So here's what we have. We have product 1 on the left and product 2 on the right. All right, these alpha cut points are in exactly the same spot, but the theta, the mean for that normal curve, for the first product is between alpha 2 and alpha 3, and now for the second product between alpha 3 and alpha 4. Right, so apparently the second product is better than the first, right, because it's going to have fewer 1-star ratings, it's going to have more 5-star ratings, and so forth. Any questions on that? Yeah, so as already mentioned, we could, but we're not going to today, we could have at least one of these variances be unknown. Yeah, just what I said. Okay. That all makes some sense? All right, so now let's build the hierarchical model. Right, so far we only have a model for our data. If we were just place a pri over the theta j's and a pri over the alphas, we would have a sort of standard Bayesian model. But now we're going to build a hierarchical model. And the way we're going to do that is that we're going to assume that these means for these normal distributions come from some distribution. Right, we're going to assume here that they come from a normal distribution with mean mu and variance tau squared. So what you should notice here is that now this is exactly the same model from chapter 5 when it talks about the normal model with a known variance. Right? Because on this slide here, a couple slides ago, right, we know the variance is 1. Right? So all we're doing is adding a prior, if you will, for the theta j's that come from some normal distribution. And now in order to make it a hierarchical model, rather than plugging in values from mu and tau squared, we're going to estimate mu and tau squared. Right? So I didn't say what we're going to use here. Use whatever you want. The only caveat here is that whatever functional form you want for the prior, one part that you have to have in the prior is to make sure that these cut points go in the order that you expect them to go in. Right? So alpha 0 is negative infinity, then we have alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5 is positive infinity. But other than that, you can have any functional form you want for the mu's, tau's, and the alphas. We're going to show the Jags code in a second. In the Jags code, I just put a uniform prior on the alphas, a gamma prior on the precision, and a normal prior on mu. Let's see, okay. So the key here is we built now a hierarchical model because we're not fixing mu and tau squared, we're estimating mu and tau squared by putting priors on them. Is it clear why this is a hierarchical model? Right, so this indicator function, it just forces there to be an, that should be a -1, haha. Maybe that's where you're confused. This should be -1 rather than equals, sorry. Right, so this just forces it to be alpha naught on the left, then alpha 1, then alpha 2, then alpha 3, then alpha 4, then alpha 5. Yep, so k -1, sorry. Yep.
Is that a way of compactly writing the last two levels of the hierarchy? We get a prior on mu, tau squared, and alpha all at the same time? Or is that?
This is just saying that you can put whatever you want here.
Okay.
Right, so typically what we'll do is we'll assume independent priors from mu, tau squared, and alpha. Right, you could do that. Right, this is just to be as generic as possible.
Okay. It's just kind of difficult to see from there why exactly this is a hierarchical model.
Right, so it's a hierarchical model because, all right, so we have these theta j's, which are the product means, right, on this sort of latent scale that we have. So we have these theta j's. If we were to just plug in values for mu and tau squared, then we would have put a prior on the theta j's. Right, so let's say we did 0, 1, not for any good reason. Right, then that would just be a standard Bayesian model. Right, we would have a posterior for theta j's, but would not be hierarchical. So it becomes hierarchical when we put a prior on mu and tau squared and therefore estimate mu and tau squared. Yes, we're also going to estimate alphas here. Either way, we would have to estimate the alphas, right, whether it was hierarchical or not. We could just fix alphas, but alphas are maybe the hardest thing, at least for me, to think about. And so I would have no idea what to fix them at. Okay. All right, so the next slide I'm going to show is the Jags code that will actually fit this model. Or, yep, that is the whole Jags code, I guess. This is the R code that fits a model in Jags. I suppose that's what I should say. And the key thing here that I wanted to show is just the model part. Yeah, okay. So I do have KJ. I see. Okay. All right. So if we look down here first at the model statement, so what I showed you on the handout for the activity is actually this data frame D. Right, this data frame D, which actually has the rows being the different products and the columns being the different star categories. Right, but the way that I introduced it in the lecture and in this Jags code, I have the transpose of that. Right, so the data here, Y, is going to be the transpose of that. So now the rows are the star ratings and the columns are the products. All right, so this top up here, this first statement is saying for each product, J, we have a multinomial distribution. We have the probability of each of the 5 categories of P, J, and we have some total observations, Nj, of that product. Right, so in the Amazon review example, right, the first product has 25 reviews, right, split up between 1 star, 2 star, 3 star, 4 star, and 5 star. Okay, so that's just a multinomial assumption. Now we have to actually calculate all these probabilities, and I could have done this a little bit more succinctly, right, so right here's another identifiability constraint that I didn't want to get into too much today. Is that you have to set one of the alphas to some particular value. So the standard thing is to set the first one to 0. The one that's not negative infinity, right? We had a negative infinity, the next one is 0. And then you estimate the others. Okay? So that's just something you have to do for identifiability. And now these alphas are different than the alphas I had in the rest of the slide, because alpha 1, yeah, okay. But nonetheless, they're still just cutoffs. So the cutoffs here are 0, then alpha 1, 2, 3, and that gets you 5 different categories. Okay? So this just does exactly what we had before, where it calculates the area under those normal curves, thereby getting each of the probabilities. And we notice here that each product has a different mean, mu j. And here a variance of 1. Okay. All right, so then now we have our prior over the mu j's. Right, they're normal with some overall mean. Nice, I should have changed this for the purpose of the slide. Okay, and some here precision, right? Tau is now the precision. Okay. And now we have that requirement that the alphas actually be in order. Right, so the next bit of code here is just doing that constraint. Right, so what we've assumed here is that the alphas are uniform on some range. Here I made the range 0 to 10. But there's no reason that the alphas have to be ordered if that was your only prior, right? If that was the only prior that you had. And so here's a Jags trick, which I do not think works in bugs, but I may be wrong, is there's a sort function. Right? So the alphas that are the actual cut points you want are these other alpha zeros sorted. And that does this constraint that we had of the indicator functions such that the alphas are actually in order. The last part we have here is then our hyperparameters, right? Distributions for our hyperparameters for theta and tau. Right, I mentioned that I used in this example a normal and a gamma. The only other thing that's a little bit tricky is that you have to here provide some initial values, because otherwise it's too easy for you to get numerical instability with, for example, having alphas too close to each other so that the probability is 0 for that category, or numerically 0 for that category, but yet you actually have observations in that category. So providing some kind of initial values is required. All right, questions on the Jags code? Yes? This is the opposite. Remember, this is the precision. Right? So this is actually a very diffuse prior. Yep. Okay. All right, so this is just the summary of the model all written down on one page. Right? Our data are multinomial for each product. The probabilities for each category of those products depend on the cut points and the mean that we have for that product in this normal distribution. And then we have some prior over our parameters.